In the previous video, we covered single linked lists as well as we described some of the limitations that come with the single implementation, with the implementation of our single linked list. We discussed the fact that although we improve the performance of arrays by adding elements in the front in O1 or constant time, but if you want to add elements at the back of the list, this is problematic because it takes like O of n. So some of the operations cannot be optimized further, which is like if we have a find, we still have to traverse the list in every way to find an element. But some of these operations like pushback, or we are going to discuss add before, they can be improved on, like the performance can be improved by changing the key implementation details of our linked list. So the first one we are going to discuss is the single linked list with tail, which is earlier we had this head that was pointing to the first element in the node, and the first node was pointing to another node, and so on, and the last one was pointing to a null. Now, if we keep a tail pointer, which like instead of having a null here, like there's another node which basically stores the tail, this allows us to improve the performance of pushback and top back. So how we can do that is, like, let's say if we want to find the last element, we can find that using um, this tail element. Or let's say if we want to find push an element in the end, like let's say if I have an element n, I want to push the element. uh, what I can do is I have access to this tail. So basically now the tail is pointing to the new node, which is I call n1, and the original tail will now, this n1's next will now point to the new tail. Or I think I've got the equation reversed, which is tail will now point to n1's next. So that's like you can still optimize that further. And that's why, like, if we add a tail pointer, some of these issues get addressed, especially the pushback and the top back one. Now, let's talk about two other ways to implement linked list, which is like when we are talking about a linked list with tails, like we saw that pushback and top back, you can get the those operations performed in constant amount of time. So we basically solve the issues of pushing back and getting the last element. But now we have added another pointer to the tail, so it's a little bit more costly. But we see that this pop back, which is like finding or removing an element from the back or adding before, is still O of n. And why that would be O of n is because although for like when we talk about, let's say, pop back, like let's say if we want to remove the last element of the link of this linked list, we know that we have a tail, but we still have a pointer to the tail. We don't have a pointer to the last element. Like the last element knows that the next pointer is the tail, but the tail doesn't know that what is the uh, last element, because we do not have an arrow like this. We just have an arrow in this direction, which is right inside. So how we can solve that issue is, like, again redesigning by something called a doubly linked list. And in this case, how the linked list would look like is we are now storing two different pointers, which is we have this head node. This points to the first element. Also, the first element points back to the previous element. And same goes on for the other list, which is you have this bi-directional approach, which is instead of storing just the next pointer, we also store the previous element. And using this, like, although we increase again, like use extra memory to store another set of pointers, this solves the issues of pop back and add before. And how it does that is, like, let's say if we talk about pop back, what we can do is you have access to the tail, and now we have also access to the previous element of the tail. So we want to insert, or we want to remove like this particular element from the list, right? Okay, 1 second. Like we want to remove this particular node from the list. So how we can remove that is we have access to the tail. Now we can remove this particular node by going to tails previous. And if we do something like tails previous, which is like if we do something like tails previous, we actually reach this particular node. And then what we can do is we can change or manipulate the pointer of this node to the next one, or we can make this point to the tail itself. So like you can do this in constant amount of time. I'm not going to go into code of each one of them because conceptually they are very easy to understand. You don't have to implement all of this, but at least do it for one of the types of linked list, which is either single, double. Also, like you have an entire project devoted to it, so I won't go into the implementations, but you are going to implement all these functions in your project. So now we can actually add elements or remove from the back, which is this pop back, in constant amount of time. But again, like we have a trade-off, which is we are storing now more in the memory because of this extra previous pointer. So the another type of linked list that is found is the circular linked list. We are not going to go into depth for these, but how it works is apart from this head and node, like instead of head and tail, what we have is the first node, the last node has a pointer that points to the first node. So it's kind of circular. And then when we are talking about doubly circular, like let's call these doubly circular, we basically have two arrows instead of one. Changing the color a little bit. So we have another previous element, and also the last node is pointing to the first, and the first node is pointing to the last. Again, like we won't be asking you too difficult questions on like doubly circular or single circular linked list, but you should always know like basic operations like how to add or remove elements in all of the linked lists we covered. So let's talk about the performance of arrays versus linked lists in general in terms of space. So when we talk about the list size, we saw that array implementations require like a fixed amount of size, while linked lists can grow as needed, which is it's pretty flexible in the size. Like when we talk about a single element, like when we are talking about a single element in the array, like just this element, it requires storage of just one item, while a linked list will require storage of one item plus the pointers, which is a bit of a downside. While this is the plus side of the linked list, which is it can grow as needed. Next, we are going to talk about the execution time. So the access is much faster in arrays. Also, like adding and removing can be a costly operation for arrays. For linked list, accessing a particular element is costly because again, we have to traverse the list. And finally, when we are talking about removal or addition, depending on the type of the linked list, we can add or remove in constant amount of time. In the next video, we are going to start with the list implementations in STL, and we are going to end the lecture in the next video.